Today we're joined by Don Peterson. Don completed his bachelor's and master's in mechanical engineering at the University of Alberta. Following, Don worked in the energy sector in maintenance and reliability roles and engineering director positions. One of his proudest accomplishments is during his 33 years of work in the energy sector, his management of personnel and engineering design safety resulted in 0 injuries to staff, contractors, or the public. In 2019, Don began his PhD in mechanical engineering here at the University of Calgary, advised by Dr. Salvatore Federico. His research interests include understanding and modeling the biological mechanisms leading to sarcopenia. He is passionate about research that improves humans' health span and also improves equipment reliability and worker safety. As a fun fact, Don has been married to his college sweetheart for 31 years, and he has 2 daughters. One is working as a curator in BC, and the other working as an emergency medicine doctor in Saskatchewan. Don is also a registered professional engineer in Alberta, and he directs 2 engineering consulting firms. As a reminder, I'll first turn it over to Don for his presentation, and then we'll have a question and answer period to follow. At that time, I'll remind everyone how to submit a question. So Don, you're welcome to get started whenever you're ready, and we're looking forward to your presentation.
Okay, thank you very much, Emily. Hello, everybody. Thank you for attending today. So my talk today is entitled Towards Lifestyle and Health Risk Management in Sarcopenia. This is my PhD subject, which I'm just been getting into under supervision of Dr. Salvatore Federico, who I'd like to thank at this time. He has taught me more about biomechanics and continuum mechanics that I thought I could ever possibly know. Appreciate that. That's of course his job. I also really appreciate the amount of time that he's given me for various family issues that have come up. I'm in a sandwich generation with elderly parents and young kids, and Salvatore has been a great support to me all the way through my studies. Okay, there we go. So what I want to talk about today is the purpose of my research. A brief review of skeletal muscle physiology, what happens to muscle mass as we age, how sarcopenia is modeled, some of my early results, conclusions from those results, and then future work. So the purpose of my work is to look at, what I want to do is develop numerical tools that can assist with managing lifestyle and health risks associated with the loss of muscle that we all incur as we age. Loss of muscle with age, that is a condition called sarcopenia. First, do a quick review of skeletal muscle physiology. So on this figure, if we start on the right-hand side, so we're going from bigger to smaller scales, and we're going from the bone deeper into the muscle. So if we start at a bone, bones are attached to tendons, tendons are attached to muscles. Inside of skeletal muscles, there are structures called fascicles. They are in the range, we're kind of in the 0.5 to millimeter scale here. We're getting smaller on the left. We have fascicles. They are surrounded by connective tissue called perimysium. Epimysium surrounds the muscles themselves. Below each of these, there's a cross section. This is in millimeters. This is in smaller scale, showing a fascicle with the individual muscle fibers in it. If we look at the fascicle and then look at an actual muscle fiber coming out, the muscle fiber is in the order of 0.1 millimeters in diameter. It's also the muscle cell. So it is the cell of a muscle fiber, the same thing. The muscle fiber has the nerves, it has the electrical connection, the motor neurons. The muscle fiber is a multinucleated cell. The little blue blotches are the nuclei, and then it has a sarcoplasmic reticulum that surrounds the muscle cell. That is the vessels that bring calcium into the cell, which causes the muscle to fire. Surrounding the muscle cell is the endomysium, and the muscle cell and the endomysium is the area that I'll be focusing on in the discussion. And again, this piece of the muscle is in the 10 to 100 micrometer kind of scale, and there's a picture of two muscle fibers below. If we zoom in further on the muscle fiber, we find that it is comprised of a whole bunch of parallel myofibrils. The myofibrils are in the 1 to 2 micrometer range. Electron microscope shot here, scale bar 1 nanometer, and the myofibrils are made up of things. The thing that's most important to us is that they're made up of sarcomeres, and sarcomeres are the basic unit of the cell that enables it to move. So let's look at the sarcomere a little more in detail. So this is the sarcomere. It's comprised of 4 main proteins: actin, which is these lines here. They are surrounded by myosin. The actin and the myosin are all mixed together in a repeating pattern, and there are cross-bridge proteins which connect the two of them and cause movement when the cell is activated. Also in the cell are 2 long proteins, nebulin and then titin, which give structure and support, and also some biological support to the sarcomere. If we look at the sarcomere in electron micrograph, we can see it's got shades of light and dark. The 2 dark bands at either end are called Z discs, and the Z discs define the extremities of the sarcomere. In the darker, we have the M band, which is an M for middle, so that's at the middle of the sarcomere. That's the structure that is the midline of all the myosin filaments. Myosin filaments come out, and you can see where the myosin and the actin overlap, where they can potentially engage and move the muscle. It's darker, and then you have other pieces, other portions where there are actin filaments and no myosin, so they appear lighter. So you get this tiger striped or zebra striped kind of pattern within the sarcomeres, which will then repeat as you go to adjacent sarcomeres. So if we look at the sarcomeres, when they're electrically activated by our thoughts, which is kind of magic when you think about it, but we think about moving our muscles, that causes a chain of electrical and chemical reactions, which causes the sarcomere to contract. Sarcomeres normally are in a resting condition shown here, and when the actin and myosin engage, they will cause the sarcomere to contract. The sarcomeres can be at a number of lengths. If they're at their resting length and they're optimally activated, we can get a maximum active contraction of the sarcomere, and that's shown in this plot, which is showing the sarcomere length from percent of optimal length. So 100% of optimal length, we get maximum contraction. As the sarcomere is activated at shorter lengths, the actin and the myosin eventually start interfering with each other, and you lose the amount of force you can generate actively. When the actin and the myosin are a long ways apart, there's just less of them to be connected. Ultimately, when they are not overlapped at all, you can activate the muscle, but you can't contract it. It can't produce any force. So the net result is the muscles produce force across their length, they are at an optimal length, they produce their maximum amount of force. So that's the active mechanism of muscles. Muscles are also composed of a number of materials and surrounded by extracellular matrix. That material is not active, but it does have passive strength, and that's shown over here on figure A. And that material is nonlinear, so when you pull on it and put it under some strain, up to 15 or 20% strain, it really doesn't exhibit much stress because there's collagen fibers that are straightening and stuff like that. So you don't get much stress on the passive material. When you start to really straighten out the collagen fibers, then just like all the other parts of our body with collagen, then the stresses increase greatly. So if you look at how the muscle completely works, you have the active portion, which is shown in as a red parabola shape in this figure. You have the passive portion, which is in blue, and then you get a total response curve in green. And at an optimum length, when the muscle is activated, the total stress in the muscle would be somewhere between 260 to 200 kPa. As the muscle is stretched, it loses active stress, but its passive stress increases greatly, and even at long lengths, even though we can't actually contract the muscle to do useful work, the passive muscle can sustain load. Okay. Property of muscles, which is both kind of expected, but is really interesting to me, is that muscles are made up of, at the nanometer level with the actin myosin molecules, and then building up into a series of repetitive structures. Many investigators over the years have looked at what kind of forces can be generated in muscles, how strong are they, and then what kind of force can they generate for a certain cross-sectional area. So investigators have looked from the myofibro right down to that level, and then looked through the fiber level and up to the fascicle and muscle level to figure out what the kind of a range of stresses can be produced. When that work is done, it's shown, and I show for three length scales here. So sort of a myofibro level, a fiber level, and a muscle level, the range of specific tensions, which is stress, produced. And what's interesting is that across this variation of anatomy, which is 6 orders of magnitude scale, the maximum muscle stress is in the range of 200 kilopascals across all those scales. There's the darker symbols are the average of the individual data points. So that's interesting and expected, because the muscle, when we look at it, it just looks like a muscle, but it is actually comprised of millions, billions of these little actin myosin sarcomeres working in parallel and series together. Okay. So what happens as we age? What happens to our muscle mass? We intuitively guess it reduces, and it does. Has been studied many times. This is just one example figure. So muscle mass over time, and people generally maintain their muscle mass in a healthy state. They'll maintain muscle mass till they're in their 4th or 5th decade, and then muscle mass both in men and women will decrease at a constant but slowly accelerating rate throughout the rest of their lives, unless they are actively trying to preserve it. But this is the general trend that's seen in people. And that loss of muscle mass is sarcopenia, it's called sarcopenia. So the prevalence and the impact of sarcopenia, about half the population over 80 has sarcopenia, which translates to about 800 million people in the world by 2025 will be considered frail. It's it's tied, of course, the muscles are tied through the tendons to bones, so they work obviously together. Um, Sarcopenia is implicated in and associated with bone loss and hip fracture, which is called osteosarcopenia, and that's the major health risk associated, or that's a health risk associated with muscle loss. It's associated with poor outcomes in people with diabetes. People who have diabetes and sarcopenia, their diabetes outcome is generally poor, and that's because of inability to dispose of glucose, decreased metabolic rate, and decreased physical activity that are hallmarks of sarcopenia. And then the loss of mobility, the loss of activity associated with sarcopenia can lead to a number of secondary mental and social and physical health consequences. So sarcopenia is very much a lifestyle impact and then a health impact, and how to manage both. And that's the kind of thing I'm interested in. The causes of sarcopenia can be grouped into, I grouped them into these three areas here. So there's lifestyle factors that would include reduced physical activity, muscle disuse atrophy, which is short-term periods of muscle disuse, for example, breaking a leg or being on bed rest because of a disease or something, and then reduced protein intake, which generally happens with older adults. Physiological conditions contribute to sarcopenia include inflammation, motor neuron loss, which the motor neuron losing those will inactivate the muscle fiber that I was talking to previously, increased anabolic resistance, and then poor blood flow to muscles. Other causes, genetic causes, and other various types of chronic illnesses. So sarcopenia has a lot of different causes. Some of those are directly controllable, and some of those are somewhat indirectly controllable. And how those fit together and how that affects muscle performance, that's the area I'm interested in understanding a bit more. Okay. So so skeletal muscles, other than being important to get us to move around and do things we want to do, they're also the largest store of protein in the body. And the protein in the body and in the muscles is usually in homeostasis, where it's being produced in one area, it's being degraded in another area, and it's being degraded just from age, or it's being degraded because constituent components are needed by some other part of the body. So normally, and as I showed in that figure where our muscle mass stays constant over the first 4 or 5 decades of life, normally that's all in balance. When we get older, tending towards sarcopenia, that balance gets lost. What this graphic is, it's showing a muscle cell, the nucleus of the cell, and then the extranuclear cytoplasm, and then outside of the cell itself. Three classes of activities will happen under sarcopenia. In the cell body and in that part of the cell, nuclear area, you can get various factors which lead to protein degradation. You can also, through lifestyle and other factors, through this part of the upper left figure, leads to inadequate protein synthesis, and then also mitochondrial damage occurs as a result of aging and other things. So you have these three things going on which all work to upset the protein balance in the skeletal muscle, and that leads to muscle atrophy. So that's looking at a cell. What does it look like in actual, like at our scale in a body? So this is a series of mid-thigh sections, cross sections, showing demonstrating what a typical thigh might look like from the age 20s up to 80s. So at the young age, of course, there's bones in the middle. The gray is the skeletal muscle, And then you can see the outline of the leg with the overlying fat and skin. The young person is almost solid muscle in their cross section, but as they age, you can see that both the muscle cross-sectional area gets smaller. The gray area is getting smaller. I know it is dark gray, but it should be the same gray as the other ones. So you can see there's quite a bit of loss of cross-sectional area, and that's associated with the protein degradation I talked to in the previous slide. The other thing that happens with the muscle is, if you look here, it's pretty consistently gray across its cross-section. As we get older, you get fat infiltration into the muscle. That both decreases the effective cross-sectional area to move objects, and then if one zoomed into where the fat and the muscles are touching, there's a lot of stuff going on there that's not helping the quality and the function of the muscle right surrounding the fat. The last thing that happens during aging is the extracellular matrix, which is very important, and it surrounds each of the various scales in the muscle structure. That extracellular matrix changes both in its thickness. It gets thicker with age, and then it also gets stiffer with age. And the particular effect of that on muscle performance is what I'll talk to in just a bit here. Okay. How is sarcopenia assessed? There's a bunch of criteria that are used to assess sarcopenia. One is low gait speed, which is showing sarcopenia in the legs, low grip strength, which is showing sarcopenia in the arms, low muscle quantity and quality, which is I talked to in the previous pictures, where the muscle gets smaller and also gets infiltrated with fat and more extracellular matrix, which is stiffer. And then distance less than 400 meters for a 6-minute walk. So a kind of a timed walk. And then a low skeletal mass index, which is a direct analog of the maybe more familiar BMI. Okay. So that's sarcopenia, that's muscles. How is this modeled? So what I've done in my work today is I'm modeling a single muscle cell, or part of a single muscle cell. Why did I choose to model at that scale versus another scale of the anatomy? Chose a single muscle because for trying to learn what I want to learn and demonstrate on sarcopenia, a muscle cell is handy because I can bring up results from the myofibril level into the muscle cell. There's stuff happening at the myofibril level that's the need to capture for sarcopenia. And it's a single muscle cell. And we have lots and lots of them, but getting results from a single muscle cell and understanding that, I can scale it easily to up towards the so that's why I chose that type of model. The model I have developed, and I'm going to show you the results of, it's 20 micrometers in diameter. 20 micrometers is a pretty small muscle cell, but that's the diameter I wanted to show. And I took a chunk of it that's 16 micrometers long. Muscle cells are multinucleated and are very, very long, certainly much longer than this, but this is the to represent the effects of sarcopenia on the muscle cell. This is the kind of length it's basically the length I needed. The picture on the left here, the diagram, this is the actual, it's a picture of an actual muscle cell. The model is considering, there's the endomysium, which surrounds the muscle cell. I'm modeling that part in, you can see it just worked out as yellow in both the picture and the model. There's basement membrane and a bunch of other stuff going on between the endomysium and the actual cell itself. That's captured at this interface between the endomysium and the cell internal structure. And then there's the whole cell internal structure with the individual myofibrils, and then all the things going on in and around them, the mitochondria, which are these red structures, All of that I'm simplifying down, and as is usually done, simplifying it down to one type of material. The material model that I'm using in this work, there's a number of material models that are used for modeling the behavior of muscles. A lot of them have been adapted from material models that have been used for other things, predominantly non-metallics in the 1940s and 50s when they started. They needed to develop material models for plastics and rubbers and such. A number of those material models were adapted to modeling biological tissue starting in the 1980s. What I'm showing the results for today, it's from a transverse isotropic Mooney-Rivlin material, which is very commonly used in muscles and other areas. It's depicted by a strain energy function. Strain energy is the amount of energy that is contained in a volume of the muscle material, and that people determine that from physical testing of muscle samples. That's a function of three terms, F1, F2, and this last term. The first term describes the first and second invariants of the distortional right Cauchy green deformation tensor. So this is capturing the deformation of the material itself. The second term is capturing the effect of the stretch along the fiber direction of the material. And then the third term reflects the volume change in the material, which is captured by the Jacobian, which is deformation, which is the determinant of the deformation gradient tensor. So that's the model that is used to, or that's a material model that I'm using to model the tissue. So I accommodate sarcopenia in the model. Like I mentioned before, the sarcopenia affects both the fibers inside the cell and the extracellular matrix by making them bigger and making them stiffer. It makes them stiffer by increasing the number of connections that occur in the collagen. The collagen, especially in the ECM, is mainly laid out to handle axial loading. That's how it is. It gets more, for lack of a better term, messed up when we get older, and it gets interconnected in ways that are not beneficial to carrying load, in a sense, and then it gets stiffer. And so capturing that, I capture that stiffening, or everybody does this kind of work, captures the stiffening by adjusting the constants in the material constants in the model. There's these constants C1, 2, and 5. They directly reflect how strong and what kind of load the material can take. These are all increased in sarcopenia models based on physical testing to reflect the impact of sarcopenia on tissues. Same thing with the bulk modulus of the material. Okay. So results from the model that I showed you. So first we'll look at, we're looking at an individual muscle cell. This muscle cell that I've modeled, it's activated internally. And the cells are really small in diameter. So the activation force on this muscle is only 15.7 micronewtons. For comparison or sense of scale, the 15 micronewton load on this is about 35% of the isometric maximum voluntary contraction force that muscle cell can handle. So it's working like a third as hard as it possibly can on its activation. It's activating internally, and then I'm also pulling the model externally with different loads, and I'm pulling on loads up to 13.2 micronewtons. So on what's happening, so that's what's the model, that's how it's loaded. And I'm looking at the normalized external load on the model, and then the resultant contraction we get. I'm looking at concentric loading, so the muscle is contracting, it has external loads it's working against where the muscle is contracting. So in this case, we have in the blue curve, this shows the healthy tissue that, again, normalized both dimensions. So it has a peak muscle contraction at a low external load. As the load gets higher, it can contract less, and then it goes down to no contraction at the maximum load. That's the blue curve, that's the healthy muscle. The sarcopenic muscle, if we look at it, it's shifted down into the left, and that reflects that the fiber and the endomysium stiffening. If we look at, so for a certain contraction, a certain constant muscle contraction, the sarcopenic muscle can carry less external load. Or if we say for the same external load, the muscle contraction is not as great. So that's what's happening at the cellular level when the fiber and endomysium stiffen. At a muscle level, something we would talk about practically in other people, it means that the we have less range of motion and we have less load carrying capacity as a result of the stiffening of the material. If we look at the other effect that's happening with the muscles under sarcopenia, I mentioned that the cross-sectional area is less of the muscle, and I showed those pictures of it. So I simulated the reduction in cross-sectional area. If you remember, the model was 20 micrometers in diameter, and I start with the reduction of 0, so the base case, and again, normalize load and contraction. So again, going from 1 down to 1, 1, 0, 0, 1 for the healthy tissue. And this one under peak external load of 13.2 micronewtons. So again, the muscle is still able to contract, but as the muscle loses cross-sectional area, as shown here, reducing 2 micrometers out of the 20, 4 out of the 20, et cetera, I get a series of curves that are going this way. And they're again reflecting that as I have less muscle cross-sectional area, one would assume that I have less load carrying capacity and less range of motion on the on that muscle cell, and that's what the model shows. Okay. So if we combine those two effects, we've got the effect of as we age, the muscles get stiffer, the extracellular matrix gets stiffer, and our muscles get smaller. So what happens when we put that all together? So again, under a concentric loading situation, the blue healthy curve, the same as we had it before, when you combine the two effects together, of course, they kind of add up in a sense. So with a 10% fiber reduction with the stiffening of the tissue, you get quite a bit of drop in what either the range of motion or the amount of load you can carry for the same range of motion, or both. And then with a 20% fiber reduction, it just gets worse. So under concentric loading, because our muscles get stiffer and smaller, we can move, the cell model shows we can move less amount, less distance, and the muscle is just a whole pile of cells together in parallel in series. So you get the same effect on the macroscopic muscle. Okay. Eccentric loading. So what the previous results were concentric loading. Now this is a summary for the eccentric loading. Again, looking at healthy tissue, a 10% fiber reduction and a 20% fiber diameter reduction. Looking at a peak external load of 94 micronewtons with an activation load of, as before, 15 micronewtons. So if I'm activating at 94, the muscle is going to get longer, which is what I want for to show an eccentric contraction. I get peak extension of 11 micrometers on the model, and then everything is normalized for load, and then resulting not contraction but extension, because we're in eccentric loading now. So in this case, the blue again is the healthy tissue, and then the orange is the 10% reduction, the red is a 20% reduction. What is interesting about this in the eccentric loading, in the corner here, I dropped in the concentric loading graph. And concentric loading showed that the muscle just lost a lot of capacity and range of motion as it got stiffer and smaller. What happens in eccentric loading, the muscle getting smaller diameter means, of course, it can carry less load, but with the muscle and the connective tissue getting stiffer, that actually helps to reduce the rate of reduction of load that we can carry. Because the muscles are stiffer, you can do an eccentric lift, or the part of the muscle that is eccentrically loaded. It doesn't, I guess you could say, it doesn't age as badly as it would under concentric loading. So where you would see this in, at a macro level, you had a box, and you asked the young person and the older person to lift the box, and the older person might have more trouble lifting the box. You ask them to lower the box in a manner that was more eccentric loading, they would be able to perform more comparably to the younger person. So conclusions from the work, the modeling to date. So the modeling can be used to understand at the cellular level the effects of sarcopenia on different types of loading. My goal is to expand that work and use it to help as input to managing lifestyle and health risks associated with sarcopenia. So from the previous graphs, so sarcopenia reduces the load carrying capacity and the range of motion of muscle fibers when we're looking at concentric loading. When we're looking at eccentric loading, the effect is less pronounced because the reduction in area and the stiffening kind of work opposite to each other. Future work. So my future work is going to be to the model I showed was for a part of an individual cell. I'm going to extend the numerical modeling to model a bunch of cells approaching the fascicle level, because then I can look at load sharing between the different cells. I'm going to model the distributed activation levels. The activation level of any particular muscle cell is dependent on a whole bunch of things, including the fiber type and what's required, what we're asking it to do, etc. So that varies with normal body function, with healthy tissue. So I want to look at that, and then also look at what happens in sarcopenia, where we get neuromuscular function degradation up to and including the neuromuscular joint doesn't function anymore, and then that you can't get active force generation in that particular muscle cell. So looking at how that all works together. I talked about how protein synthesis and degradation are out of balance in sarcopenia. The effect of that on muscle capacity is known, and that's what I showed here. But the underlying, what actually happens to cause the, what's from the ground up, what happens to impact the stiffness and impact the loss of muscle tissue that shows up as sarcopenia. There's been less work done on that, and that's what I'm focusing on. And then the other thing that there's been a lot of work in general done is the impact of therapeutic interventions. The main therapeutic intervention for sarcopenia is strength and conditioning training. Of course, there's endless research on that, less so on what actually, the actual quantified effect of different regimes on protein synthesis. So looking at how that would affect protein synthesis, which would help offset reduction of cross-sectional area leakage. And thank you for your time and attention. And that is completion of my talk. Again, want to thank Dr. Federico and my supervisory committee for supporting me through all this work.
Thank you, Don.
Thank you. How long?
Great. At this time, Don, if you are willing to stop sharing your screen, please.
Yes.
And I would just ask everyone in the audience that if you're comfortable, perfect. Everyone in the audience, if you're comfortable, please consider turning on your camera to allow for better discussion. To ask Dawn a question, you can use the raise hand function by clicking on reactions on the bottom of your Zoom screen. And if you're unable to use the raise hand function, you're also welcome to type your question in the chat box and I will read it aloud. Matt, please ask your question.
Thanks. Really enjoyed the presentation. I had a question and obviously defer to you on this, but some of my sort of reading through this in looking at more how fast muscles can contract, it seems to be equally, if not more of an issue as we age, that we lose that rate of force development, muscle power capacity. And I'm just wondering if you could just comment on that with your research in terms of how the shortening velocity might factor in alongside your range of motion and your strength capacity.
Yeah, thank you. Yeah, excellent question. And the answer at this point in my work is, I've read that sarcopenia affects the force velocity curve. The model that I showed, that model I've used the extent I can use it for, which was showing what I did. It isn't set up well for doing the velocity piece of it, the dynamic piece. So I'm working, the next phase is going to be working on a dynamic model. Which if the dynamic model works, it should show that the force velocity curve gets depressed just like the range of motion strength curve.
Can I ask you just one more little follow-up question?
Absolutely, please.
And this is really from a practical standpoint, but it sure seems that when you look at, you looked at your figures where you look at loss of strength as we age, and you kind of see that slippery slope where around 45, people start to go off the back end of the curve. Are you aware of any ways that with sort of extending from your modeling that we could sort of model those changes early on to maybe identify somebody down the road who might be at future risk so that you could have sort of early intervention on these things? Any comments there?
Yes, and that's exactly what I'm thinking about. That I showed they have those clinical criteria for sarcopenia.
Yeah.
That define sarcopenia, and I suspect what happens in reality in doctor's office now, people go in and, gee, I'm weak, I'm having troubles doing what I like to do, and the doctor will just do an initial assessment, or they might do those tests, but they're all lagging indicators.
Sure.
It's sort of like, okay, here, go do some grip strength. You got crappy grip strength, and yeah, your muscles are, you got sarcopenia, your muscles are not in great shape. And depending on the individual, and then I'm thinking a lot about lifestyle as well,
right,
because it impacts lifestyle, and impacting lifestyle affects mood and health, and mental health and everything. And then there's a physical impact, risk of fracture beyond that. What I don't have the answer, but what I would like this to feed into it, and there's a bunch of people working on bits and pieces of this, right? That going in and doing a scan of some sort with technology that is sort of exists when a person's in their 20s and 30s and 40s, and they're in their 40s and they want to rock climb till they're 90, or they're in their 40s and they're more sedentary, but they're happy. What are their lifestyle requirements, expectation going forward? So given that, how can we arrest the slope of that curve? Or if it's going to happen anyways, get that curve pushed up. By you want to keep doing what you're doing when you're 80, you got to work hard now so you can deal with that curve. So the vision, of which my work is just a tiny little piece, I'm going to focus mainly on the modeling piece, but the vision would be take that modeling piece build it into some type of tool that a GP could, would be willing and would be useful to use to assess muscle quality in a person over time, both relative to absolutes and then equally importantly relative to their lifestyle expectations. So that's the vision. My work is gonna be looking at the numerical piece of it. I don't think there's full data that I can just go get somebody and look at all their life. If I had lifelong data on somebody, I could do more. That long-winded answer sort of get to the point, describe what I'm thinking.
Yeah, it was great. Thanks.
Thank you. Thank you.
Benno, please ask your question.
I
think you just need to unmute, Benno.
That's almost like sarcopenia. Very nice presentation, thank you. One of the problems in sarcopenia is if you want to train your muscles, that the muscles don't react as nicely as they did 50 years ago. Do you have with your model the possibility to try to understand that and try to provide some solutions for that question?
That's my thinking. I don't have it now.
How do you plan to do it?
Because I know that there's lots of research I've been reading on modeling protein synthesis through strength conditioning. There's lots of stuff on that for healthy people. I don't know. I'm going to look and see if there's I'm answering your question by restating your question. How is protein synthesis in a 65 or 70-year-old? How does that compare to a younger person? That I don't know.
And can one influence it?
Yeah, and can we influence it? If I can get it, I can model it, and maybe it'll show that, like you had said, that it's much harder for older people to recover strength because the whole system isn't as robust as it was when they were younger. Which if I can model that will again shift the emphasis for early detection and preconditioning relative to what you wanted to be doing when you're older. So that's what I'm thinking. I don't have the answer. The answer is part of the scope. So my thinking is to building on what's out there now on increasing protein synthesis with training, and see what's there in training of older athletes, and seeing what I can learn from that. Again, it's the exploration.
Thank you.
So thank you.
Brent, please ask your question. Maybe Brent has a question.
His hand's up, but he's muted, or he looks muted.
I'll maybe ask a question while we wait. Oh,
Sure.
okay, sorry. I thought maybe they figured it out. I'll ask a question while we're waiting for Brent. Could you maybe paint more of a picture of how you would envision this being used as a clinical tool? Like, how early in life should people start evaluating some of these metrics? How often would a patient and a clinician be touching base on this? Things like that.
Don't know for sure. There is, and my idea is not just light bulb for me. I'm just reading what other people are starting to poke around at that. In California, UCLA, there's researchers there that are starting to do like doing a scan for muscle quality. There's more and more of that coming along. That's working from the clinical end of it. And then there's other people that are working kind of where I am at kind of the modeling end of it. And then the two are going to eventually reach across and meet together. I would think they can meet together in 10 years or so, just guessing. Because what that needs is it needs some sort of handheld scanner, which maybe can attach to an iPhone, that can do an assessment of muscle quality. Yeah, in some area that's, again, it's medical stuff, so it's got to be practical for a GP to use so that you can get a baseline of muscle quality. And then the GP will have to know what the person's background likes are and their expectations for how they age. So those are the pieces of it. I don't have it put together, and I certainly am self-aware enough that I'm not going to put it together. I'm just going to do my little chunk of it. But what I think the vision would be, a person once they get to say 30, when people get tied up with, potentially with families and jobs and stuff, and they first start to get less active potentially, maybe every 5 years kind of thing, to build a baseline of how their MSK system is functioning. And I think it would go, because muscles in themselves don't do anything other than contract. So it's, of course, the whole MSK system, bone cartilage assessment as one is going along. And that's as far as I've gotten so far.
That's great. Brent, I'm not sure if you're able to get your microphone working, but would you or anybody in the room like to ask a question?
Can you hear me now?
Yes.
Okay, excellent. So I'm pretty familiar with the Mooney-Rivlin constitutive model, and we use that to model tendon quite frequently. What I don't understand, we poll on it, and we basically see how what happens. What I don't understand is what you do when you say we activated this internally. Can you kind of explain what you mean by that? When you, like, I assume you're talking about you're prescribing some kind of internal pressure or something like that, but I was just a little unsure.
Yeah, no, you got it. It's a there's a short answer and a long answer. I won't do the long answer because even my short answers tend to be long. But the short answer, for purposes of the model, which is to demonstrate the idea, the internal activation was a prescribed force on the model. So I worked backwards from a target stress related to a force, and I put that stress on the model to simulate the contraction.
Okay, but it's a node, or it's a surface at the end of the model, and you're pulling on it, or it's
exactly.
doing something internally.
No, the codes that are out, there can have that wired in where you can do it internally. There are limitations to doing that, which is why I didn't use those. So for the model, I just prescribed it as an external force that gave the same kind of pressures and calibrated it that way.
Okay, thank you.
Yeah, no, thank you for that.
Arash, please go ahead.
Thank you for the great presentation. So in one of the figures, I think it was figure 11, that you had this capacity of the muscle versus the reduction in the muscle size.
Yes.
So there was in 10% reduction, there was close to 30%, 10% reduction in muscle area was close to 30% reduction in the capacity of the muscle. And then when we go a bit more, and when we have like 20% reduction in muscle area, then this reduction in the capacity of the muscle does not change that much. Like, looks like there's a nonlinear effect there.
Yeah.
I was
Yeah.
wondering if it's that correct, then can it be used somehow? Like, let's say, okay, if 10% is like, it's a lot, but then after that, then it wouldn't matter much.
Yeah, absolutely. So the figure you're talking about is this one here. That's figure 11, which showed the reduction in capacity with reduction in what that was. What I modeled was reduction in diameter, and so the 10% reduction in diameter is more cross section than the 20. So that's part of the reason. That's part of the reason for it. And then it does get nonlinear just because it's a nonlinear system.
Yes.
But yeah, that the first time I did that, I looked at that and I thought, yeah, that's interesting. I knew it wouldn't be twice as much because it's diameter. I'm reducing diameter, not total area. But then I looked at it and I thought, yeah, there's a big drop with a small reduction in area, which is not good practically, right? It means it makes it harder to manage because you have to be able to measure and understand smaller reductions in cross section.
Yes.
So yeah, I saw that and I thought about that, and what I gleaned from that is, you don't lose much if you just lose it from the outside. You don't lose much before you use a lot of strength, which is unfortunate, right?
Yeah.
But again, I don't have. There's more fidelity that I got to build into it to understand it better.
Thank you.
Thank you.
Venus, please go ahead.
Hi, very nice talk. Thank you. So I'm wondering about your thoughts regarding the single fibers themselves. So because you have been talking about a change in the cross-sectional area, and this reduces the capacity of the muscle to produce force. But what about a single fiber? So if I take a single fiber, do you think its capacity to produce force is reduced? And I think people, and you have touched a little bit on this, and on protein synthesis and degradation. So I would like you to talk a little bit more about it.
The model that I showed and what I did work on, it was of muscle fiber dimensions. So the model was the size of a muscle fiber. It was 20 micrometers and 60 micrometers long, which is as long as I needed to model it. I'm assuming that because 20 micrometers, I'm starting to get between continuum and distinct modeling, but I'm relying on the constant stress with cross-sectional area to justify modeling down to that level. So that was the assumptions. That was the assumptions there. I want to feed up from a lower level when I do some other modeling to validate that, because I'd like the and the single fiber model that I did using the literature's constants for the material model, I did reproduce results from larger chunks of tissue to the fidelity that I want right now. And that fidelity will increase as I get further along. But no, so that's what I've done at this point. And I know how much you know about muscle fibers, so my little assumption versus your huge depth on like the intricacies of it. Yeah, absolutely.
Okay. But, this is what I thought. So do you believe that in sarcopenia there is also a decrease in the stress produced by the fibers?
To this point, Yeah, I would suspect that. I can't quote that yet, simply because I haven't gotten far enough into it yet.
Okay, I see.
What I've read to this point is reduction in area, the changes in the protein, the pathways, and the sifting of the mechanical properties. So that's what I've been looking at to this point, because that's from my background, that's the first and easiest things I can model, of course.
Okay, perfect. Yeah, thank you very much.
And then when I start thinking about all that kind of stuff, I'll come and bug you, because you can teach me some stuff that I don't know. Thank you.
Thank you.
Are there any other questions from the audience? Great. If there are no other questions, thank you again, Don, for sharing your work with us today. It was really interesting. And thank you all for signing on and asking questions. Next week, we have another speaker. We'll be hearing from Natalie Young, and she will be presenting on feedback responses must disengage from postural control to initiate rapid movements. So I hope everyone has a great week, and I hope to see you all again next week. Thank you again, Don.